Right now, at this very moment, there's an object hurtling through our solar system at 137,000 miles per hour that should not exist. Not here, not travelling along this trajectory, and certainly not behaving the way it is. What I'm about to share with you isn't speculation, it's data. Hard numbers collected by the most sophisticated instruments humanity has ever pointed at the sky. And those numbers are telling us something that makes even the most skeptical scientists pause and reconsider everything we thought we knew about what travels between the stars. On July 1st, 2025, at precisely 0347 Universal Time, the ATLAS survey telescope in Rio Hurtado, Chile, detected something moving against the backdrop of distant stars. The observatory's automated alert system flagged it instantly, not because of its brightness. It wasn't particularly luminous, but because its velocity vector made no sense. It was travelling too rapidly and along the wrong path. Within 18 hours, observatories across 3 continents verified what the ATLAS team had already suspected. This wasn't one of ours. It originated from somewhere else. They designated it 3I/Atlas, the third confirmed interstellar object to enter our solar system. The I stands for interstellar. That's the straightforward part. Everything else about this object contradicts our expectations about what interstellar visitors should look like. Let me explain the observational network that's been monitoring this thing since July. We're not discussing amateur astronomers with backyard telescopes. The ATLAS system itself represents a NASA-funded network of 4 robotic telescopes, specifically engineered to identify near-Earth objects and potential impactors. It surveys the entire visible sky every 48 hours. When ATLAS made the initial discovery, the Minor Planet Center immediately dispatched an alert to the global astronomical community. Within 72 hours, pre-discovery observations were retrieved from the archives. The Zwicky Transient Facility at Palomar had recorded it as early as May 22nd. The Vera Rubin Observatory, just becoming operational with its unprecedented survey capabilities, had inadvertently imaged it during validation runs in late June. NASA's Transiting Exoplanet Survey Satellite, TESS, had documented it as far back as May 7th, when the object was still 6.4 astronomical units from the Sunday. Consider that timeline. TESS captured it when it was beyond Jupiter's orbit. Already active, already producing a glow. Comets aren't expected to be active that far out. Water ice doesn't sublimate significantly until a comet approaches much closer to the Sun, typically inside 3 astronomical units. Yet 3I/Atlas was luminous and outgassing at more than double that distance. The James Webb Space Telescope directed its infrared instruments toward the object in early August. What Webb discovered was a carbon dioxide to water ice ratio of 8:1, the highest ever measured. For comparison, typical solar system comets display ratios closer to 1:10. This thing's composition is reversed. It's like discovering an iceberg composed primarily of dry ice with only traces of water mixed in. That's our first impossible detail. A comet from another star system with chemistry that implies formation, temperatures, and conditions fundamentally different from anything in our stellar neighborhood. The Hubble Space Telescope obtained detailed images on July 21st. Those images revealed something that captured every astronomer's attention. The comet had a dust plume, yes, but the geometry was off. Instead of the classic tail pointing away from the Sun, formed by solar radiation pressure pushing gas and dust backwards, 3I/Atlas displayed what observers described as an anti-tail, a jet of material pointing toward the Sunday, 10 times longer than it was wide. The Nordic Optical Telescope in the Canary Islands monitored this feature through July and August. Then in September, something shifted. The anti-tail transformed. it became a conventional tail pointing away from the Sunday. That transformation occurred as the object approached perihelion, its closest point to our star. Now, anti-tails aren't impossible. They've been observed before on solar system comets, usually as perspective effects or when dust particles with specific size distributions get left behind in the comet's orbit. But the scale and persistence of what 3I/Atlas exhibited was unusual. More unusual was the timing of the transformation. It happened exactly when solar heating should have reached a threshold, almost as if something inside the object responded to hitting a specific temperature or radiation flux. These are the observations. I'm not telling you what to conclude. I'm telling you what the instruments recorded. Multiple independent observatories, different telescope systems, different imaging techniques, all witnessing the same sequence of events. Let me provide you with the hard numbers. The object is massive. Analysis of its trajectory through September 23rd, utilizing 4,022 observations from 227 observatories worldwide, revealed something remarkable. There was no detectable non-gravitational acceleration. When comets outgas, they generate thrust, material jets off the surface preferentially from the sun-facing side, which creates a force. That force should push the comet slightly off a purely gravitational trajectory. It's called the rocket effect, and we observe it on every active comet in our solar system. 3I/Atlas showed none of that. Zero deviation from a gravity-only path, despite losing 25 kilograms of water per second, according to Webb's measurements. For that to happen, the object must be massive enough that the outgassing thrust is negligible compared to its total mass. The calculations place it at over 33 billion tons, minimum. That corresponds to a solid nucleus at least 5 kilometers in diameter. That's 1,000 times more massive than Oumuamua, the first interstellar visitor. It's 1,000,000 times more massive than Borisov, the second interstellar object. Here's the terrifying part. Given the limited reservoir of heavy elements in interstellar space and the size distribution we'd expect for debris ejected from other planetary systems, we should have detected roughly 100,000 smaller interstellar objects before finding one this large. We've only found 2. The statistics don't work. Unless 3I/Atlas isn't typical. Let's examine 3 scenarios. Scenario 1. This is exactly what it appears to be on the surface. A massive comet ejected from another planetary system millions or billions of years ago, wandering through the galaxy until gravity brought it into our solar system. The unusual chemistry reflects formation in a different stellar environment. The anti-tail behavior results from a combination of rotation state, active regions on the nucleus, and dust grain size distribution that happens to produce observed geometry. The mass explains the lack of non-gravitational acceleration. Everything fits if you allow for enough uncertainty in the parameters. This is the conservative interpretation. It requires no new physics. It simply expands the range of what we consider normal for interstellar objects based on a sample size of 3. Most astronomers would default to this position. It's safe, it's consistent with naturalism. It doesn't require invoking anything beyond known mechanisms. Scenario 2. 3I/Atlas is a natural object, but its properties are so extreme that it represents something we haven't seen before. Perhaps it's the core of a disrupted planet rather than a typical comet. Perhaps it formed in the outer reaches of a stellar system very different from ours, maybe around a low-mass star, or in a system with an unusual heavy element, abundance. Its chemistry and behavior are teaching us something fundamental about the diversity of planetary formation environments across the galaxy. Under this scenario, studying 3I/Atlas becomes critical for understanding how planets form in different stellar contexts. It's a messenger from a world we could never visit, carrying information about conditions around stars dozens or hundreds of light years away. The object is still natural, but it's showing us nature has a broader palette than we suspected. Scenario 3. Let's be precise about what I'm suggesting here, because I want no ambiguity. Under this scenario, 3I/Atlas is not entirely natural. Some component of it, whether the entire object or something attached to it, has been engineered. This doesn't mean aliens are piloting a comet toward Earth. It means a sufficiently advanced civilization, aware that comet-like objects regularly pass through planetary systems, might use such objects as carriers, embed instruments within them, let them follow natural trajectories shaped by gravity and solar radiation, indistinguishable from natural objects to casual observation. Only upon detailed analysis would subtle anomalies emerge. Composition slightly off, trajectory too perfect, activity patterns responding to environmental thresholds with suspicious precision. This scenario doesn't require faster than light travel or violation of physics. It requires patience, long-term thinking, and technology capable of surviving interstellar journeys lasting millennia. A civilization could seed their local stellar neighborhood with thousands of such instrumented objects, letting gravity do the work of distributing them. Most would drift through empty space forever. A few would happen to pass through systems containing planets. Fewer still would pass through systems where intelligent life had developed technology sufficient to detect them. If you wanted to study emerging technological civilizations without direct interference, this is how you'd do it. You'd wait for them to notice you. And noticing requires they develop sophisticated astronomy, spectroscopy, trajectory analysis. By the time they can recognize the anomaly, they've already crossed a threshold of technological development. They're ready for the information. Am I saying 3I/Atlas is alien? No. I'm saying the data we have doesn't cleanly fit scenario 1, and scenario 3 provides testable predictions that we should be monitoring for. That's all. Science works by proposing hypotheses and designing observations to distinguish between them. Dismissing scenario 3 without examining it is as unscientific as jumping to it without sufficient evidence. So what would constitute evidence favoring scenario 3? Multiple things. First, detection of materials or isotopic ratios that can't be produced by any known natural astrophysical process. Second, trajectory changes inconsistent with gravitational dynamics and natural outgassing, especially if those changes serve to keep the object in our system longer or redirect it towards specific planetary bodies. Third, electromagnetic emissions at frequencies or with modulation patterns that suggest artificial generation. Fourth, geometric structures visible in high-resolution imaging that can't be explained by natural fracturing or erosion patterns. Fifth, sudden release of smaller objects from the main body, especially if those objects adopt different trajectories suggesting independent propulsion. None of these have been observed yet, but we're watching, and we have the instruments to detect them if they occur. Let me give you the countdown. Where we are right now, today is October 25th, 2025. 3I/Atlas passed perihelion on October 29th. It's currently behind the Sun, from Earth's perspective, unobservable. On November 11th, it emerges back into our eastern pre-dawn sky. Telescopes 8 inches or larger should be capable of picking it up, though it won't be visible to the naked eye at any point. The IAWN observation campaign officially begins November 27th and runs through January 27th, 2026. That's the window where the coordinated global effort will monitor its post-perihelion behavior. What should we look for? First, any fragmentation. If the solar heating at perihelion exceeded structural limits, the nucleus could break apart. We'd observe multiple objects where there was one. That would strongly support the natural comet hypothesis. Second, changes in brightness or outgassing rate. If activity increases beyond what thermal models predict, or decreases faster than expected, that tells us something about the internal structure and composition. Third, the emergence of non-gravitational acceleration. As the object loses more mass, eventually thrust from outgassing should become measurable. When that appears, and how strong it is, constrains the true mass and size. Fourth, any trajectory changes inconsistent with gravitational dynamics and known outgassing forces. If 3I/ATLAS maneuvers, if it shows course corrections that can't be explained by natural processes, that's a game changer. On December 19th, closest approach to Earth, 1.83 astronomical units. Not close by comet standards, but close enough for detailed spectroscopy. Multiple observatories will point their instruments toward it, ground-based infrared telescopes, space-based ultraviolet and X-ray monitors. We'll obtain the best compositional data during that window. In February 2026, we should receive data from Jupiter's JUICE spacecraft, which attempted observations in November. JUICE was on the opposite side of the Sun from Earth during its viewing window, so the data had to wait for transmission. Those observations could show 3I/ATLAS in a highly active state post-perihelion, revealing what's left after the close solar encounter. On March 16, 2026, Jupiter flyby, 46 million kilometers. While that's too distant for the planet's gravity to significantly alter the object's trajectory, it's within range for Jupiter's magnetosphere to interact with any plasma in the comet's coma. Radio observations during that time might detect electromagnetic signatures, finally, any deployment events. If 3I/ATLAS were to release smaller objects, probes using the Sun's gravity for course changes toward inner planets, tidal forces from solar heating would separate their trajectories from the main body over a period of months. By spring 2026, any such separation would become apparent. We'd observe new dots in the sky, moving independently, but all traceable back to 3I/ATLAS at perihelion. That's what we watch for. Now, here's where it gets personal. I've spent my entire career working at the intersection of theoretical physics and cosmology, thinking about parallel universes, higher dimensions, the nature of space and time. But this object currently moving through our solar system brings the question of our place in the cosmos into sharp, immediate focus. Not as an abstract thought experiment, but as something we can point telescopes at, something that's here, right now, carrying information we can extract if we ask the right questions. The Fermi paradox asks why, if intelligent life is common in the universe, we haven't seen any evidence of it. Where is everybody? 3I/ATLAS doesn't answer that question, but it sharpens it. If this is a natural object, it tells us that interstellar space is rich with large, ancient bodies, carrying chemical signatures of planetary systems vastly different from ours. That diversity itself is profound. It means the universe manufactures a wider range of environments than we've sampled through our own solar system. If some of those environments produce life, that life will be even more alien than we've imagined. If 3I/ATLAS is something else, if any component of scenario 3 is correct, then the implications cascade. We're not alone. We're being observed. We've been found. And the method of contact is subtle, embedded in natural phenomena, requiring us to develop sophisticated technology and analysis before we can even recognize it for what it is. That's a level of sophistication that suggests intelligence operating on timescales and with patience completely outside human experience. I'm not here to tell you what to believe. I'm here to present what we know, what we've measured, and what remains unexplained. The scientific process requires skepticism. It requires us to exhaust natural explanations before invoking extraordinary ones. But it also requires intellectual honesty. When the data doesn't fit comfortably into existing models, when multiple independent measurements all point towards something unusual, we have an obligation to follow that evidence wherever it leads, even if it makes us uncomfortable, especially if it makes us uncomfortable. 3I/Atlas will be observable from Earth starting in mid-November. The global astronomical community will be watching. Professional observatories, university research teams, amateur astronomer networks. The data will be public, the measurements will be independently verified. By Christmas, we'll know more about post-perihelion activity. By spring, we'll have tracked its encounter with Jupiter. By this time next year, we'll have a complete dataset spanning the object's entire passage through the inner solar system. That data will either reinforce the natural comet interpretation, adding this massive visitor to our catalogue of interstellar objects and expanding our understanding of planetary system formation across the galaxy. Or it will force us to confront the possibility that the universe is paying attention to us. I want you to stay on the timeline as this unfolds, because whether 3I/Atlas is a comet or something more, the observations over the next few months will be historic. We are watching in real time as an object from another star system passes through ours. That alone is extraordinary. The fact that it's generating scientific controversy, that it doesn't fit neatly into our expectations, makes it even more valuable. Subscribe so you don't miss the updates as new data comes in. The IAWN campaign results, the JUICE observations, the December close approach measurements. This is science happening at the frontier, where our models meet reality, and sometimes reality wins. What's your take on this? Are we witnessing sophisticated pattern recognition, our evolved tendency to see agency and intent in natural phenomena? Or are we finally detecting the first unambiguous signs of contact, hidden in plain sight, waiting for us to develop the tools to recognize it? Leave your thoughts in the comments, because the beauty of science is that it doesn't care what we believe. It only cares what we can measure. And right now, the measurements are telling us something we didn't expect. The clock is running. 3I/Atlas is already on its outbound trajectory, heading back toward interstellar space. In a few years, it will be too far and too faint for our telescopes to track. This is our window, our one chance to study this object in detail before it disappears back into the cosmic darkness it came from. Whatever 3I/Atlas is, whatever secrets it carries, we have months, not years, to extract them. The universe has delivered something to our doorstep that challenges our understanding. How we respond to that challenge, how carefully we examine the evidence, how honestly we acknowledge what we don't understand, will define this moment in the history of astronomy. Are we alone? That question has haunted humanity since we first looked up at the stars and wondered if anyone was looking back. 3I/Atlas doesn't answer that question. Not yet. But it's forcing us to sharpen how we ask it, to develop better tools, to think more carefully about what evidence would actually convince us one way or the other. And maybe, just maybe, to prepare for the possibility that the answer might arrive not as a radio message or a flying saucer, but as a massive ball of ice and rock from another star system, following a trajectory that shouldn't quite make sense, carrying chemistry that doesn't quite match, moving through our neighborhood exactly when we've developed the ability to notice. The data is coming. The telescopes are watching. The next few months will tell us more. Stay curious, stay skeptical, and keep your eyes on the sky, because 3I/Atlas is out there right now, and it's not done surprising as yet.